Hi, there are four laws to thermodynamics, and there are some of the most important laws of all physics. The laws are as follows. The zeroth law is so named as it came after the other three. Laws 1, 2 and 3 had been around for a while before the importance of this law had been fully understood. It turned out that this law was so important and fundamental that it had to go before the other three. And instead of renaming the already well-known three laws, they called the new one the zeroth law and stuck it at the front of the list. But what does it actually mean? So the law states if two thermodynamic systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. So let's make it simple. So if we have this thermodynamic system here, which is a cup of water, the water has the same temperature as the room temperature, means they are in equilibrium. And if we have another glass of water, same amount of water, so another thermodynamic system has the same temperature and is in equilibrium with the room temperature, means these two glasses of water are in equilibrium with each other too. So basically A equals to B, C equals to B, means B and B are equal each other too. This may seem so obvious that it doesn't need stating, but without this law, we couldn't define temperature and we couldn't build thermometers. The first law of thermodynamics basically states that energy is conserved. It can neither be created nor destroyed, just change from one form to another. So the total amount of energy is an isolated system, is conserved. Remember, we talk about this system, we're talking about closed systems. So the energy in a system can be converted to heat or work or other things, but you always have the same total that you started with. So let's have an analogy for that. And for that, I am going to actually show you a magic trick. So here we have 4 coins. They are representing energies. So I place one in this hand, one in the other hand, one in the top here, top of the finger, and one in the top of the other one. If I don't hold this coins with my fingers here, and when I turn my hand upside down, they're gonna fall. So that shows the importance of the conservation of energy in closed systems. So if I place this again here and the other one in here, so need to be closed system. So I take them inside. So inside my hands are closed system. Now I'm going to transfer energy within the closed system to the other hand. So from my right hand to left one. So 3, 2, 1, and the energy is transferred. I've transferred one energy, means I should have one energy remained here, which is one coin here. And according to the laws of conservation of energy, I should have 3 in this hand to have the total of 4. So here are our other 3. I will teach you this magic trick in one of my next videos. The second law, this is possibly the most famous and important laws of all science. It states the entropy of the universe tends to a maximum. Or we can say the entropy of an isolated system, not in equilibrium, will tend to increase over time, approaching a maximum value at equilibrium. Before I explain this law, I need to explain what entropy is. We need to know entropy in the phase space, but I think knowing the entropy would be enough to understand the second law for beginners like me. So entropy is a very important thing in the realm of thermodynamics. It's the core idea behind the second and the third laws and shows up all over the place. Essentially, entropy is the measure of disorder and randomness in a system. Let's have examples for that. Imagine you have a container of gas molecules. If all the molecules are in one corner, then this would be a low entropy state because they're highly organized. As the particles move out and fill up the rest of the container, then the entropy or disorder will increase. Imagine that this kettle here is a closed system, and there is no energy transfer between this kettle and the outside. So we have the energy, which is a form of electricity, come through the cable, is the electric kettle here. So we have some water inside the kettle and the air inside. So the air and the water both are in a thermal equilibrium now, have the same temperature. So now if we send energy to go through the kettle, which is electricity, let's see what will happen. So the electricity has turned to thermal, and thermal start to give boiling the water. So we can see here is the movement of the water particle, that is in terms of kinetic energy. And as you can see, because the water and the air inside the kettle, they weren't in a thermal equilibrium, or they were, but after it heats up, they weren't. So therefore, that energy in some form is passed to the air particles, adding to the kinetic energy of those particles and increase the entropy within the system. The third example we can have is when you have a ball flying through the air. So first is starting as its energy being organized, for example, the kinetic energy of the motion, but as it moves through the air, however, some of the kinetic energy is distributed or dissipated to the air particles, so the total entropy of the system has increased. But we know the energy is conserved, so that's what we're talking about, the closed system. So the total amount of energy before and after is equal. So in other words, entropy either stays the same or gets bigger. The entropy of the universe can never go down. But the problem is, this isn't always true. If we think about our example of atoms inside the box, then all of them being in one corner is a highly ordered system, and so we'll have a low entropy. And then over time, they will move around, become more disordered and increasing the entropy. But there is nothing stopping them, all randomly moving back to the corner. It's incredibly unlikely, but not actually impossible. So it's possible for them to go back again in the corner and making it all. So now that we did talk about the entropy, we need the reference point for measuring the entropy. So that's where the third law comes through. The third law provides an absolute reference point for measuring entropy, saying that as the temperature of a system approaches absolute zero, which is minus 273.15 degrees Celsius or 0 Kelvin, then the value of the entropy approaches a minimum. The value of the entropy is usually 0 at 0 Kelvin. However, there are some cases where there is still a small amount of residual entropy in the system. So when you heat something, depending on what it's made of, it takes a different amount of time to heat up. Assuming that power remains constant, this must mean that some materials requires more energy to raise the temperature by 1 Kelvin. 1 Kelvin is actually the same as 1 degree Celsius. If you think about it, this makes sense. A wooden spoon takes a lot longer to heat up than a metal one. We say the metal is a good thermal conductor and wood a poor thermal conductor or insulator. The energy required to raise 1 kilogram of a substance by 1 Kelvin is called its specific heat capacity. And you know the formula for that. You have learned that, or you will learn that in GCSE physics. So the third law of thermodynamics, as temperature approaches absolute zero, the entropy of a system approaches a constant minimum. So I hope you have learned about the laws of thermodynamics and you enjoyed this video. I'll see you in the next video. Bye.